that, okay, like, okay. So why this must be true? Poincare inequality. So here's a proof. So let's take a U from H1 naught. Okay. H1 naught. Sometimes you also hear that, okay, you know, these are, so such conditions are, you know, that with Banach and bound, we call them a Dirichlet boundary condition. You have Dirichlet, you might have not had that, because the others will not. They are going to be also Dirichlet boundary conditions. Anyway, so U is in H1 naught, okay. So we claim that for each such U, if you, okay, integrate, okay, J was the integration operator, if you remember. So if you integrate the weak derivative, you're gonna get U. Okay, you're gonna get U. And once we have this, you know, we are done actually. And why we are done? Because we did just the result, which I'm going to quote again now. Okay. Okay. So here's the thing. So indeed, so here's a, if the weak derivative of this integral, so if this is true, I'm not saying this is true actually, I'm saying this must make sense. I'm going to just, so that, okay. So indeed, if you know, the weak derivative of the derivative gives you double prime, U prime actually, and U prime minus U is a constant. Okay. Here we have used what do you call corollary 10.6. What was corollary 10.6? Corollary 10.6 says, yes. So if this is true, just think about it. If this is true, that means that Ju prime minus U NH prime is 0. In it? In weak sense. So if this is true, then this must be true. And if this is true, so it's like, so the derivative of this guy, weak derivative of this guy is 0, then I can say that this must be constant. Okay. Now consider this expression. At what do you call t equal to a. Okay. All of these are depending on time, so consider this expression at t equal to a. So at t equal to a, use 0.
Yes, by.
Okay. By definition, because u is from h1 naught. Okay. And at t equal to a, what would be this integral actually? So recall, what was Ju? So the Ju was the integral a to t, okay, of u of x dx, right? So if I evaluate now, so if I have a prime here, I'm going to have a prime here. So if I evaluate at a, so I need to put the a here actually. 0. So what's it going to get? You're going to get to 0 actually. So in other words, at t equal to a, this expression, so it's like a Ju prime minus u vanishes. 0. Okay? So here's the thing. But this is a constant actually. This expression is a constant. So what do you mean by that? So its values for all times is same. So if at one instant it's 0, then it would be 0 at all instants actually. Just think about it. So here's the thing. So I'm saying that I have a function. Okay? I have a function which is constant actually. And I come to know that at one instant it's equal to 2.
Yes.
That means since it's constant it should be 2 every day. So it must be there. So if this is 0, what does it show? You got this. You got this what you want. Okay? Now if this is true, hence what you get this, this Ju prime of Q. In other words, you integrate the weak derivative, you get U back at it. Now I'm going to say, let's compute the norm of U in L2 sense. Okay? So the norm of U in L2 sense.
हमने ये assume किया है
What?
indeed if वाली के बाद statement है Ju prime का एक derivative U derivative ये हमने assume किया है मतलब ये proof हमने शुरू कहाँ से किया मुझे ये समझ नहीं आया
I'm saying that this is a constant type. Why this is a constant?
तो हमने use कर लिया है वहाँ
Because every element in U can be expressed as the integral plus constant actually. So U is in H1, so it can be expressed as J of weak derivative plus constant. So this is what that we saw yesterday. So in other words, this expression makes sense actually. This expression makes sense. So this is what known to us actually. This is what known to us. So if this is known to us, then this must be true as well. Are you getting the point? We did a corollary.
Yes, sir.
There was a lemma, we saw actually. It says that every U and every F in H1 can be expressed as sum of an integral plus some constant actually.
Yes.
So every F in H1 can be expressed as sum of an integral plus constant. Then the integral and minus different must be a constant actually. And I'm saying that this constant is 0 at one instant, so it must be 0 at all time. This shows that this must be true. So in other words, for H1 naught, this must be true. And you need to be careful. This is not in general true actually. So you got this phi equal to 0 because of this not condition actually.
Boundary condition.
Because of this not condition. Because we know that at t equal to a, U of a is 0. If we don't have this, then only this would be true. We can't say that what would be that constant. Are you getting the point? You have to be.
If U of A is 0, why is J of U prime minus?
Okay. Let's say it again. So if U of A is 0, so I'm evaluating both points at A. And I'm saying that U at A is 0 and this is also 0. Why this is 0? Because I just said that what was the J of F? So the J of F is the integral from A to T of f of x dx. Okay? So in other words, so it's like at time t. But if I evaluate this at A, we're going to have an integral from A to A. Okay? And once upon a time we learned that if you have such a situation, your integral is 0.
Here we have U prime U derivative.
What do you mean by that? So in other words, I'm saying that this is true. So I'm saying that substitute A here. Substitute A here. You're going to get a 0. And F is arbitrary. No matter what F you should have. F is arbitrary. No matter what F you should have, this must be true. Are you getting the point?
Yes.
Okay. So what does this show? that this guy at A is 0. But we say that this guy in general is a fixed constant. So if this is 0 at one instant, then it must be 0 at all instants. And hence, we should have this. Are you getting the point? And then U is same as, the norm of U is same as L2 norm of Ju prime. Okay?
Since J is a linear bounded operator.
Yes, this is what that I was about to say next, is that since we know that J is a linear bounded operator, from where to where?
L2 to CAB.
L2 into CAB. Okay. Was it CAB?
Yes, sir.
Okay. CAB. So therefore, but we also proved that inequality basically that this can be estimated by,
by boundedness.
by the U prime of L2 norm. No, I mean this is true in general actually. So JF of L2 norm is some constant, okay, is some constant times U prime of L2. And this is what that you wanted actually. You need to keep a track of the previous results. Okay? Where we have this result, I mean if you want to recall it.
Chapter 4.
No, there's no need to do the chapter 4. I mean we saw this in the theorem. Okay. 182. So you have theorem 10.81. Yes. Yes. Okay. So you have to. It's from theorem 10.8 actually. Okay. Anyway. So what we are saying is this. Let's recall, let's quickly review the key thing that we would like to do. So what I'm saying is that for every U in H1, there exists a constant B minus A such that this inequality is true. Okay? What is this inequality saying? That this is saying that the L2 norm of U can be estimated by the L2 norm of U prime. Okay? And we say that let's take U from H1 now. Now, if U is in H1, then every such a U can be written as the integral plus some constant. So every U is such a U which is in H1. We know that we saw last time the result that it's equal to the integral plus some constant, and hence this expression is true. In other words, this expression is constant for all times. Okay. Now, if this expression is constant for all times, let's evaluate this expression at A. And we say that, so it's going to be Ju prime of A and U of A. But since U is from H0, so this must be 0. And Ju of A is also going to be 0 by definition. So in other words, this is 0 at time A actually. So since this is constant, so it must be 0 at all times. And hence we say that this is equal to this. And hence, if I want to evaluate L2 norm of U, I have to evaluate the L2 norm of U prime. We saw inequality yesterday that I can estimate this by what do you call some constant times L2 norm of the input. And the input is U prime. Okay. So the Poincare inequality is true. Now once we have this, we have almost everything to prove the existence and uniqueness of the Poisson problem. So let's do the proof. Existence of uniqueness. Okay? Existence and uniqueness. Okay? Alright, so let's do existence and uniqueness. So let's begin. So for a given f in L2AB, we have to find a solution. In what space? In H1 not space. Okay. And we want to find a U in H1 not that satisfies such that what it should satisfy.
Unique.
And unique actually. We want to find a unique U in H1 not such that it satisfies that psi U in H1 naught is equal to psi F in L2 naught. Okay? In other words, such that psi prime U prime in L2 is equal to what? Psi F. Okay? For all psi in psi what? C1 naught. So this is the test functions. Okay. So in order to do so, I'm going to use the Rees-Fresher theorem now. And now you're going to see that the Rees-Fresher theorem is going to help you out. So what is it? So let's define. Let me define a phi from H1 naught, okay, into C by as phi of V equal to Vf in L2. So when I'm not mentioning anything, it's like L2. So if I have something else, I'll mention it in specific. Okay? So I defined it in this way. So in the Rees theorem, what you need?
So we need G, such that it is inner product.
So, but what are the assumptions of Rees theorem? Rees-Fresher theorem.
So if phi is linear
And bounded.
bounded function, then
So
it can be expressed
If
as
phi is linear and bounded,
then it can be expressed as inner
so it's
product.
obviously linear. I don't need to prove it. So let's see the bounded. So phi of V is in C. Okay. So this must be equal to 1. F
जो हमने choose किया
norm.
F जो हमने assumption में choose किया
Yes, F is from the So I can estimate this by Kashi Schwarz. Norm of V. Okay. So, in 2 norm and F in 2 norm as well. Agree? But Poincare inequality tells me, Poincare inequality tells me that I can estimate this by V prime of
C times
some constant times this. Are you getting the point? Alright. So let's not get rid of the problem. Shall I get rid of this proof? I think we don't need it. We need reciprocity. So if this is the case, okay, what does this quantity is equal to? This quantity, V prime of 2 norm. So anything prime of 2 norm is that thing H1 norm. I would say that this shows that my phi of V is less than or equal to, okay, the energy norm of V, okay, obviously C times norm of F norm times H1. Okay. Now since F is fixed, so this norm is also a fixed number. So this whole is like a constant actually. Okay. And what does this show? This shows that phi is bounded. This is what that you wanted. So for the boundedness, you need to do what? You need to estimate the output in the terms of the norm of A and H1. So this is what that we did. Okay. So you have this in H1 norm, and this implies that phi is bounded. Okay. And obviously linear. Hence by Rees-Fresher theorem, what are you going to get? There exists a U. Okay, such that this phi of V can be written as a duality. What's that? The inner product of what? Of this U
Inner product V.
inner product with V. Okay. And for all and in what norm? And in what inner product? In H1 inner product. Okay. So what's H1 inner product? I haven't defined it. But the meaning of H1 inner product is that if I have UV and I have H1 not inner product,
H1 not.
so it must be U prime, V prime inner product into norm.
H1 not होगा ना सर ये यहाँ पर भी H1 not ही और वो जो आपने डिफाइन किया था उसका
Okay.
So U कहाँ होगा वो H not 1 to 1.
So this must be true. U is going to, there exists a unique U in H1 not
Domain में.
such that its duality with an arbitrary element, okay, of H1 not, okay, is equal to what do you call phi of V. Are you getting the point? This is what that it's going to show. Now, wait a minute. What does this equal? We know it by the definition. So this is same as VF actually, or FV. VF. Are you getting the point? And what we got on the other side? So if I write it explicitly, it must be same as U prime, V prime, and that is equal to what do you call VF. Are you getting the point? Alright? That you know. And can you see something now? What you can see? So you got a point in H1 naught which satisfies your required equation. And this is true. Okay. So this is true for all V in H1 naught. Okay. So if this is true for all V in H1 naught, it must be true for all V in C1 naught actually that you want. So what do you have is a more actually than the equality. So this is true. So what you wanted is true.
We wanted to find U for every F. So we'll define this transformation for every F.
Which Yes, if you have been given a particular f for which you want to solve the problem, you have to define this. Okay? Are you getting the point?
सर यहाँ पर f जो है वो
L2 का element. Okay, so what we showed that for every L2 we find a U, there exists a U from H1 mod which satisfies this equation, and hence this U which is in H1 naught is a solution of your, what do you call, abstract Poisson problem. Now what's the point of doing all that?
सर
What's the point of doing all that? Now essentially I would say there are two schools of thought in mathematics. So one who are interested in what? Doing, what do you call, very practical kind of work. For example, you are doing differential equations, like doing engineering stuff. So you model things, okay, and you come to a particular differential equation and you solve it through, you know, analytically or numerically, and you get a solution, and you get a graph and everything, and so on and so forth. And the other school of thought is this, who are not interested in a particular problem, who are interested in an abstract equation. This is a very abstract equation. Okay? So if this is true, if this exists in, what do you call, that if a solution exists in this sense, you know, with some additional things we can show that the solution of the same problem exists in the classical sense as well. So this is more than what you are doing previously. So it's like more serious stuff. Okay. It's very, very serious. Some people are interested in, in doing this kind of problem. That's a pretty abstract problem. You're not solving it through some equations actually. You're solving it through analysis. You're saying that for sure, you know, such a solution exists. Existence to uniqueness is a big problem. Are you getting the point? Okay. So this is what the solution of the Poisson problem is. You can ask also now that, okay, you know, if I, so